Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on Chapter 7. Now we've made it to the fifth objective, and the title of the fifth objective is heat capacity. So far in our lecture, we've talked about both heat and temperature. We said that heat is the flow of energy that occurs as a result of a difference in temperature. And when energy is transferred as heat, the direction of energy transfer is always from hotter object to the colder object. We've also made the point that heat is not the same as temperature. Temperature is a measure of the kinetic energy of a system, whereas heat is a measure of the transfer of kinetic energy from one system to another. Now, although heat and temperature are not the same, we can use the change in temperature to calculate heat. And the quantity that ties the two in together is heat capacity. Now, heat capacity is defined as the amount of heat required to raise the temperature of a substance by 1 degree Celsius. Now, you might also hear the term specific heat capacity. This is defined as the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Additionally, you might hear the term molar heat capacity. This is the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. Now, if you know the heat capacity of a substance, you can calculate the heat using the following equation. Here we have Q, which is heat. This is equal to mc delta T. M is mass, C is your specific heat capacity, and delta T is your change in temperature. Now here, C, it can be in units of Celsius or Kelvin. Also, temperature here can be in Kelvin or Celsius since we're talking about difference in temperature. Now, this is a point of confusion for a lot of students, so let me show you why it doesn't matter if you take the difference of temperature, delta T, of two temperatures in Celsius or two temperatures in Kelvin, you're going to get the same difference. So let's say that we have an initial temperature of 15 degrees Celsius and a final temperature of 30 degrees Celsius. If we're trying to calculate the delta T, we're going to do final minus initial. This is going to be 30 minus 15, and that gives us a delta T of 15. Now, if we were to convert these temperatures into Kelvin, 15 degrees Celsius is 288 Kelvin, and 30 degrees Celsius is 303 Kelvin. So we went ahead and converted these Celsius temperatures into Kelvin. Now, if we take the delta T for these temperatures in Kelvin, we have final 303 minus initial 288, and notice we get the same number for delta T 15. So if you have two temperatures, initial and final, in Celsius, you don't have to convert them to Kelvin to take the difference. And same goes for vice versa. If you have two temperatures in Kelvin, you don't have to convert them to Celsius to take the difference. You would get the same answer for delta T regardless, as long as both temperatures have the same scale and they're either in Kelvin or Celsius. Now, one more important thing I want to point out before we go ahead and jump into an example problem. There's one important thing to remember for the MCAT here, and that is the specific heat of water. The specific heat of water is 4.18 joules divided by grams multiplied by Celsius. Now, this is equal to the same quantity but with Kelvin instead of Celsius. In addition, we can also have the heat capacity for water in units of calorie per gram per Kelvin. And sometimes using the value with the units calorie actually makes your calculations a little bit easier. We're going to see that in an example problem here shortly. But the specific heat of water in units of calorie is just 1 calorie per gram per Kelvin. So these are the values for the specific heat of water that I highly recommend you commit to memory. Now with that, let's go ahead and jump into an example problem. This example problem reads, when 30.9 kilojoules of heat is added to 750 grams of an unknown liquid, the temperature rose from 25 degrees Celsius to 72.9 degrees Celsius. What is the specific heat capacity of the unknown liquid? Express your answer using the units joules per gram per Kelvin. Now, to solve this problem, we're going to use our equation Q equals mc delta T. Now, in this problem, we're actually given Q, we're given the heat, that's 30.9 kilojoules, and we're given the mass, that's 750 grams, and we're given the initial and final temperature. Now, the goal of this problem is to figure out the specific heat capacity, which is C. So the first thing that we want to do is rearrange this equation to solve for C. When we do that, we get that C is equal to Q over m delta T. Now, keeping this in mind, and keeping in mind the fact that we want to express our answer using units of joule per gram per Kelvin, let's go ahead and convert our Q, our heat, from kilojoules to joules. Now, this is an easy conversion. We just have to multiply this number by 1,000, and that gives us 30,900 joules. Now, for mass, we have 750 grams. And then for delta T, we're given the initial and final temperature. So we can just go ahead and take the difference between the two temperatures, 72.9 minus 25 degrees Celsius. Now, remember, we don't have to convert this temperature to Kelvin to take the difference because the delta T is going to be the same whether we keep these two temperatures in degrees of Celsius or we convert them to Kelvin. So we can just pretend that we're going to figure out our delta T from our temperatures in Celsius, but our answer is still going to be in units of joules per gram per Kelvin because we would get the same delta T if we went ahead and converted this temperature from Celsius to Kelvin and did the math this way. So regardless, what we get for our answer is going to have units of joules per gram per Kelvin. It will also be the same value in units of joules per gram per Celsius. So if we plug this into our calculator, what we're going to get for C is that it's going to be equal to 0.860 joules per gram per Kelvin. And that is our answer for the specific heat capacity of this unknown liquid. Now, the next thing we want to do is ask, well, how do we go about measuring energy change? And this actually helps us move into our next objective where we're going to discuss calorimetry. Calorimetry is the technique that we use for measuring the heat involved in a chemical or physical change. An instrument that's used for measuring the energy transferred as heat is called a calorimeter. Now, there are two common types of calorimeters. We have constant volume calorimeters, and we also have constant pressure calorimeters. We're going to discuss both, starting off first with the heat flow under constant volume conditions. Now, constant volume calorimetry is often done using a device known as a bomb calorimeter. A constant volume container is built in a way that it can withstand high pressure without exploding, hence why it's called a bomb calorimeter. Now, at its core, calorimetry revolves around the principle of heat transfer. When a substance undergoes a chemical reaction or a physical change within a calorimeter, heat is either going to be absorbed or released. And the measurement of this heat change provides insights into various thermodynamic properties of the substance. Now, in a constant volume condition, the volume doesn't change, which means that delta V is equal to 0. Now, this implies that no work is done because we know that work is equal to minus P delta V. In a constant volume calorimeter, delta V is equal to 0, so work is also equal to 0. So that means that under constant volume conditions, the change in internal energy is going to be due or equal to the heat that is absorbed or released at constant volume. So again, the change in internal energy of the system can be directly equated to heat under constant volume conditions. So we can use a little subscript of V to denote that this is heat that is absorbed or released under constant volume conditions. So then when a reaction occurs in a bomb calorimeter, two important points here is the energy released or absorbed is entirely due to the heat changes since no pressure or volume work is done. And this makes bomb calorimeters, this is point 2, especially useful for studying combustion reactions where considerable heat is released and can be measured accurately without the complications of volume changes. So that is constant volume calorimetry. What about constant pressure calorimetry? So let's discuss heat flow under constant pressure conditions. Here we're going to measure heat flow while holding the pressure constant. In experiments where pressure remains constant, such as a coffee cup calorimeter, the setup is designed to be open at the top to the atmosphere. And this means that the pressure inside the calorimeter is going to be in equilibrium with atmospheric pressure, thereby remaining constant throughout the experiment. Now, under constant pressure conditions, the energy changes in the system can be expressed with the following equation. Delta E, the change in internal energy, is due to heat plus work. But here what we're going to do is we're going to expand the term for work to minus P delta V. And we're also going to denote that this heat term is under constant pressure conditions. So we're going to add a little subscript of P right here. Now, looking at this, we have our delta E is equal to Q. This is the heat added or removed at constant pressure minus P. P is the constant pressure. Delta V is the change in volume. Now, what we can do to this equation right here is we can rearrange it to solve for Q. When we do this, what we get is the following equation that you see here. QP is equal to delta E plus P delta V. Now, this equation indicates that the heat flow at constant pressure can be determined by measuring the change in internal energy and accounting for the work done by or against the atmospheric pressure due to volume changes. Now, measuring the work can be difficult, and we can get away with it by introducing a new thermodynamic property called enthalpy. Now, enthalpy is represented by the letter H. It is also a state function, just like delta E is, just like internal energy is, and it can be expressed as delta H is equal to delta E plus P delta V. Now, this also allows us to say that the definition of enthalpy exactly matches the definition of QP. So delta H is equal to QP under constant pressure conditions. Again, let me repeat this. This is true under constant pressure conditions where the change in enthalpy equals the energy flow as heat. Now, enthalpy simplifies the calculation of heat changes under constant pressure because it inherently accounts for any work done to volume changes. And so by definition, at constant pressure, the change in enthalpy directly corresponds to the heat added or removed from the system. And this relationship is really important for us. Now, if a process releases heat, then delta H is going to be negative. The sign of delta H is negative, and that means the reaction is exothermic. In contrast, if heat is absorbed, this is going to be an endothermic reaction, and the sign of delta H is going to be positive. Now, we're going to elaborate on endothermic and exothermic reactions here shortly, but first, I just want to tackle a practice problem. So let's go ahead and jump into this example problem here. This problem asks 1 cup containing 100 grams of water at 300 Kelvin is mixed into another cup containing 200 grams of water at 450 Kelvin. What is the equilibrium temperature of the system? Assume that the pressure is sufficiently high that it avoids boiling. So we have this one container with 100 grams of water, and this is going to be at 300 Kelvin. And we have this other container that has 200 grams of water, and it is at 450 Kelvin. And we're going to go ahead and mix these two liquids together. Now, when the two liquids mix, they undergo thermal exchange. And remember that when energy is transferred as heat, the direction of energy transfer is from the hotter object to the colder object. And so here, the heat that is given off by one liquid is going to equal the heat that is absorbed by the other liquid. So we can go ahead and write the following expression. This is where we want to start. Now we have our definition for heat. Heat is equal to mc delta T. So we can use this expression to replace our terms for heat, and this way we'll be able to calculate the equilibrium temperature. What that gives us is the following expression. Here we have our mass for the cold multiplied by the specific heat capacity of water multiplied by the change in temperature. And this is going to equal the mass for the hot cup multiplied by the specific heat capacity for water multiplied by the difference in temperature. Now here we can't forget the negative sign. We're going to add it to the delta T sign. Okay, now what we can do next is start to plug in some of the values that were given in this question stem. Some things to keep in mind. Because we are solving for the final equilibrium temperature of a mixture, we can actually use any value for C as long as we are consistent for both liquids. Now, both liquids are water, and we talked about the specific heat capacity for water in units of joules and also in units of calories. In the units of calories, it's going to be really easy because it's just equal to 1 calorie per gram per Kelvin. So we're going to use this value for both C's because both liquids are water, and 1 is just such an easy number to work with as opposed to 4.18. Also, we know what the mass for the colder water is. It's 100 grams. And we know what the mass for the hot water is. It is 200 grams. In addition, we know the final and initial temperatures here for both cups. So let's go ahead and expand this writing to include some of these values that we know. So for the colder cup, we have 100 grams. Specific heat capacity, we're going to use 1 calorie per gram per Kelvin. And then the temperature final minus our temperature initial, which is 300 Kelvin. This is going to equal the mass for our water in the hotter cup. This is 200 grams. We are using the same heat capacity because they are both cups filled with water. And then here we have minus T final minus T initial, T final minus T initial for this cup is 450 Kelvin. Now we can go ahead and distribute this negative sign, and that way what we can write is 450, if we distribute the negative sign, we get minus TF plus 450 Kelvin. We can rewrite this to just be 450 Kelvin minus TF, just so that this is easier to read. And now all we have to do is isolate TF, right? Because this is our final equilibrium temperature. So how are we going to do this? Well, let's do a little bit of math. On this side right here, we have just this 1 on both sides. So let's just ignore this, right? We're just multiplying by 1 essentially for the specific heat capacity. So let's just erase it just to make the calculations easier. All right, they both cancel out because they're the same value on both sides. So now on the left side, we have 100 grams multiplied by TF minus 300 Kelvin. So what we're going to do is we're going to distribute this 100 to both terms. So now what we have is 100 T of F minus 100 times 300, that's 30,000 grams times Kelvin. We're going to write this as calorie here. Okay, on the right side, we have 200 grams multiplied by this, and we're going to distribute it. So what we have here is 200 multiplied by 450. We get 90,000 calories minus 200 multiplied by minus TF. We get minus 200 T of F. Now what we can do is move all of the variables, the TF variables, to one side. So we're going to go ahead and move the TF to one side by adding plus 200 TF to both sides. So now on one side we have 300 T of F. This is our final equilibrium temperature. And then we're going to move the calories over to the other side. So we're going to add 30,000 to both sides. And now we get that 300 T of F is equal to 120,000. Now we can divide by 300 for both sides so that we can isolate the final temperature. Now this is a really easy calculation. We can cancel out the zeros here. We have 1,200 divided by 3. This is going to be equal to 400. So T of F is 400 Kelvin. And just like that, we figured out the equilibrium temperature of our system. And the math was really easy because we were smart about the value of C that we were using. And in addition, even if we chose the other value, since we have the same heat capacity on both sides for water, those values would have canceled out anyways. So we could have put in 4.18 joules per gram per Kelvin, and the math will still be easy because we can just cancel them out on both sides since that value appears on the left side and on the right side. So the final answer is 400 Kelvin. Wonderful. Now, the next thing we want to continue to elaborate on is endothermic versus exothermic reactions. Earlier, we said that if a process releases heat, then the sign for delta H is going to be negative, and that reaction is considered exothermic. On the other hand, if a process absorbs heat, then the sign of delta H is going to be positive, and that process is going to be considered endothermic. Now, in the context of chemical reactions, any energy diagrams serve as a powerful tool to illustrate the energy transformations that occur from reactants to products. So they provide a graphical representation of the energy changes during a chemical reaction, and they give us a picture of the energy landscape from reactants to products. So let's actually explore how these energy changes are represented and interpreted in energy diagrams for both endothermic and exothermic reactions. So let's start off with exothermic reactions. In an energy diagram for an exothermic reaction, such as the combustion of methane, for example, the reactants start off at a higher energy level compared to the products. So as the reaction proceeds, it moves downhill energetically, reflecting the release of energy into the surroundings. And the difference in energy between levels, in energy levels between reactants and products, this corresponds to the delta H, the heat released. Then we have endothermic reactions. In an endothermic reaction, the energy diagram shows the reactants at a lower energy level than the products. And so the progression of the reaction requires an uphill climb in energy. So it's absorbing heat from the surroundings. In both types of diagrams, the highest point on the energy path, this represents the transition state, this point of maximum energy that the system must overcome to proceed from reactants to products signals a transition state. Now, the peak is indicative of the activation energy that's required to initiate the reaction. The lower the activation energy, the faster the reaction. So again, to summarize, in an exothermic reaction, energy is released into the surrounding. You're going to have a delta H with a negative sign. In an endothermic reaction, energy is absorbed. Delta H is going to have a positive sign. Now, processes in which substances change its phase is also either endothermic or exothermic. So in this figure right here, it helps us kind of break this down. So the first thing that we can talk about is going from a solid to a liquid. This is melting. This transition from solid to a liquid is endothermic because energy must be absorbed from the surroundings to break the organized structure of a solid into the less organized structure of a liquid. Now, the reverse process going from a liquid to a solid, freezing, this is an exothermic reaction. And it's exothermic because energy is released when a liquid forms a structured solid. That leads to the release of heat. Now we can also talk about going from a liquid to a gas. This is the process called evaporation, and it is also endothermic. It requires heat to overcome the attractive forces between liquid molecules, allowing them to move freely as a gas. What about the opposite process, going from gas to liquid? This is called condensation. The process of gas turning into a liquid is an exothermic reaction, and this is because energy is released as heat when gas molecules lose energy and move closer together to form a liquid. There's also the transition from solid to gas. This is called sublimation. This process is endothermic. It requires energy to overcome the forces holding the solid together and becoming a gas. The opposite process, deposition going from gas to solid, this is exothermic. This releases heat as gas molecules slow down and bond together to form a solid. Now we can ask the question, why are some phase changes endothermic and others exothermic? And the answer lies in the energy changes that are involved in breaking and forming bonds. So in endothermic reactions, what's happening is we absorb energy because the energy needed to break the bonds in the initial state is greater than the energy released when new bonds are formed in the final state. And so the system absorbs heat to make up this difference. What about exothermic reactions? Exothermic reactions release energy because the energy released from forming bonds in the final state is greater than the energy required to break bonds in the initial state. And so that excess energy is going to be released into the surroundings as heat. So that's why some phase changes are endothermic and others are exothermic. Now, to further explore the practical implications of these phase changes and the energy involved, we can begin to analyze heating curves, which graphically represent how the temperature of a substance changes as heat is added. So let's go ahead and talk about it. A heating curve graphically represents how the temperature of a substance changes as heat is added. And this is really important for understanding phase changes and the energy that's required for these transformations. So when you have a compound that's heated, its temperature increases until it reaches a phase change point, such as the melting or boiling point. Now, at these points, the temperature remains constant despite the addition of heat, despite continuous heat addition. And that's because that energy is used to change the phase of the substance rather than increasing its temperature. Now, to fully understand heating curves, we're going to use two fundamental equations. We're going to use Q equals mc delta T, and we've talked about this equation already. And the second equation is Q equals ml. This is a new equation. We're going to talk about it here shortly. Let's review Q equals mc delta T. This calculates the heat that's added or removed when a substance's temperature changes without a phase change. And in this formula, Q represents heat, M is the mass, C is the specific heat capacity, and delta T is the change in temperature. Now, the equation at Q equals mc delta T, it applies to all of the sloped segments of the heating curve where the substance is in the solid, liquid, or gas phase and the temperature changes. Now, on the other hand, we have this other equation, Q equals mL. And this equation actually calculates the heat involved in phase changes where the temperature remains constant. And you can easily remember that because there's no temperature term in this equation. Q here is heat, M is the mass, L is the latent heat. The latent heat is a general term for the enthalpy of an isothermal process. You can think of it as the heat required to change the phase of 1 gram of the substance without changing its temperature. It will usually have units of calorie per gram. Now there's two types of latent heat. We have latent heat of fusion, delta H fuge. This is for solid to liquid transitions. And we also have the latent heat of vaporization for liquid to gas transitions. Now this equation applies to all of the flat segments in our heating curve. So now we know when to use the MCAT equation for all of the sloped segments of the heating curve. And now we know when to use the Q equals mL equation for all of the flat segments in our heating curve. Now, understanding these processes and equations allows for the precise calculations of the energy changes that are involved in heating substances and their phase transitions. And really, the best way to learn how to use heating curves to your advantage for solving problems is to jump into a practice problem now. And that's exactly what we're going to do. Now, this problem says, what amount of energy is required to change a 90-gram ice cube at minus 10 degrees Celsius to vapor at 110 degrees Celsius? Now, we're also given a lot of information here. We're given the specific heat capacity for water in its liquid form, the specific heat capacity of water as a solid, and the specific heat capacity of water as vapor, as a gas. We're also given the delta H of fusion and the delta H of vaporization. Now, before we hop into this problem, I want to make one quick note about our new equation, Q equals mL. Now, this is the mass, so it's going to have units of grams, and latent heat has a unit of calorie per gram. So what you notice is that grams cancel out, and your final answer is going to have units of calorie. You can also use this equation to calculate heat by having moles multiplied by delta H of fusion or vaporization. N is going to have units of mole, and delta H of fusion or vaporization is going to have units of either kilojoules per mole or joules per mole. And what you notice here is that then the units of moles will cancel out, and your final answer for heat is going to have units of joules or kilojoules. So you can use either form of these equations to solve the segment for your heating curve, that flat segment for your heating curve where phase changes occur. And we're actually going to take advantage of this form of this equation in this practice problem. So let's go ahead and write down what we know and what we need to figure out for this problem. In this problem, we know we're starting with an ice cube, so water in its solid form. And then we're heating it up all the way to 110 degrees Celsius where it will become water vapor. The first thing that we want to do is draw out the heating curve for water, and this should be easy because we know the freezing and melting point, and we should also know the condensation and vaporization point. And we can use that to kind of sketch out our workflow and all the equations we need to use to calculate the total energy required for this change. So let's go ahead and start there, right? We know that we have solid water at minus 10 degrees Celsius, and it will continue to be solid up until it reaches 0 degrees Celsius because that is the freezing melting point for water. Then at this point, there's a phase change that's going to happen, solid to liquid phase change, where all the heat that is added doesn't affect the temperature, but it will help in creating that phase change from solid to liquid. Then after the phase change has occurred, now we have liquid water. And we have liquid water up until we reach 100 degrees Celsius. This is the condensation / vaporization point. This is where we're going to have liquid and gas. All right, liquid to gas phase transition. And then, of course, at this point, all the heat that's added doesn't change the temperature. It is just there to help the transition between phases. And then after all of the liquid has been converted to gas, then we're in the gas phase up until we get to 110 degrees Celsius. So here's our heating curve for our problem. Now at each point we can assign what equation to use. Here we're going to use our Q equals MC delta T equation. Here we're going to use our ML equation, or depending on the information we get, moles times delta H. We're going to use this form actually because we are given the delta H of fusion and the delta H of vaporization. Then in this segment here where it's a liquid, we're going to use Q equals MC delta T. Here in the liquid to gas transition, we're going to use Q equals N delta H. And remember, for this segment right here, we use fusion. For this segment right here, we use vaporization. All right, it's important to know what delta H to use in which segment. And then for the last segment here, when we have converted all the liquid water to gas water and we're just heating it up until 110 degrees Celsius, we're going to use our Q equals MC delta T equation. Okay, so we're going to do 1, 2, 3, 4, 5 expressions that we're going to solve for the 5 segments of our heating curve. And the energy we get for each part, we're going to sum all of them up together to get the total amount of energy that's required to change 90 grams of ice cube at minus 10 degrees Celsius to vapor at 110 degrees Celsius. So that is our workflow. So let's go ahead and start with segment 1, this one right here. We're going to note it as Q1 equals MC delta T, and this is for our solid phase. So we're going to put solid phase for each of these as subscripts to remember what we're dealing with here. Now we know we have 90 grams of ice. We also know the specific heat capacity for ice, for water in its solid form. It's 2.18 joules per gram per Kelvin. So let's write that down, 2.18. And then what is our delta T? We're starting off at minus 10 degrees Celsius. We're ending off at 0 degrees Celsius. That's this segment right here. So our final temperature is 0, and we subtract that from our initial, which is minus 10. So what we have here is 90 multiplied by 218 multiplied by 10. All right, so these are the numbers that we're dealing with. Now what we're going to do is we're going to round this to 2 so that this calculation is really easy to do without a calculator. Now we have 90 times 2, that's 180, and then 180 multiplied by 10. That's going to be 1800 joules, or in other words, 1.8 kilojoules. So that's our first segment. That's our step 1. Now our step 2 is going to be for this phase change from solid to liquid. So in step 2, we must convert the ice into liquid form. And during this phase, remember, there will be no temperature change. So our equation for step 2 is Q equals ML, or in other words, we can do number of moles of water multiplied by the delta H of fusion. And we're actually going to use this form because we're given delta H and not L. Now, how much moles of water do we have? We're going to have to convert the 90 grams of water we have to moles using the molar mass, and the molar mass of water is 18 grams for 1 mole. You can think of this as kind of like 900 over 20. We can approximate it as such, and that's about 5 moles of water. So we're going to do this kind of approximation. So N is 5 moles, and delta H of fusion, we're given this in the problem, 6.02 kilojoules per mole. So let's go ahead and plug this in. That's going to give us 5 moles of water multiplied by 6.02 kilojoules per mole. And that gives us as a final answer here, 5 times 6, you can think of it like that, is equal to 30 kilojoules. Okay, so let's write this down and then begin to erase some of our work. So for step 1, we got 1.8 kilojoules. For step 2, we got 30 kilojoules. Let's go ahead and work on step 3. Now, step 3 is where temperature changes, all right? We're heating up our liquid water. So what equation are we going to use for step 3? We're going to use our Q equals MC delta T. So for step 3, we're going to use Q equals MC delta T. And this is for liquid water. So I'm going to write L next to all of the variables so we remember what variables we're using here. Now, again, we still have 90 grams. That's good. What about the specific heat capacity for liquid water? We're given that as well, 4.18 joules per gram per Kelvin. So let's go ahead and write that down, 4.18 joules per gram per Kelvin. Okay, that's what we're given. And then here, what's our final minus our initial? Our final is 100 degrees Celsius because that is where we reach our condensation vaporization phase change. And our starting temperature is right here, 0 degrees Celsius. So 100 minus 0 is just 100. So the math that we're working with is 90 times 4.18 times 100. And we're going to go ahead and round this to about 4. So now we have 90 times 4, that's 360, multiplied by 100, that's 36,000 joules, which is equal to 36 kilojoules. So for step 3, we calculate 36 kilojoules. Now, step 4 is a phase change. Step 4, we vaporize the water. Again, no temperature change will occur during this phase change. So we're going to use our handy dandy Q equals ml equation, which is equal to number of moles of water multiplied by delta H of vaporization. Very important to remember that in this phase, liquid to gas, we use delta H of vaporization. Delta H of fusion is for your solid to liquid transition. Please do not confuse the two because that would be a silly mistake to make to get this problem wrong. So just keep that in mind. All right, so Q equals ml equals number of moles multiplied by delta H of vaporization. So we calculated number of moles, 5 moles. Now what's delta H of vaporization? We're also, thankfully, given that. It is 40.67 kilojoules per mole. So 40.67 kilojoules per mole. So we can kind of think of this as 5 times 40. We're doing some approximations to make the calculations easy without a calculator. 5 times 40 is 200. So step 4, 200 kilojoules. Let's write that down. 200 kilojoules. And now we can erase this work and do our last and final step. And this is where we have all the liquid now converted to gas, and we're just heating it up from 100 degrees Celsius to 110. So in this last segment right here, we're going to be using our Q equals MC delta T, and this is for our gas. So the mass is the same, 90 grams. So we're going to write that down. And then what's the specific heat capacity for water vapor? We're also given that it's equal to 2.0 joules per gram per Kelvin. Okay, good to know. So let's go ahead, write that down, 2.0 joules per gram per Kelvin. And then what's our delta T? Well, our final temperature is 110 degrees Celsius. Our initial temperature for this segment is right here at 100 degrees. So we have 110 minus 100, and that gives us a difference of 10. So now what we're multiplying is 90 times 2 times 10. This is 90 times 2, which is 180, multiplied by 10, that's 1,800 joules, or in other words, 1.8 kilojoules. All right, so now we have the energy for each segment. The total heat that is required for this whole phase change from beginning to end, our Q total, is going to be the sum of Q1 plus Q2 plus Q3 plus Q4 plus Q5. And that's going to look like 1.8 kilojoules plus 30 kilojoules plus 36 kilojoules plus 200 kilojoules plus 1.8 kilojoules. And if we sum this up, you're going to get 274.8 kilojoules. Now, this is an easy addition, but if you want to make it even easier for yourself, you can most definitely round these values. So this can be a 2, and this can be a 2, and we can round those two, and that makes it easy. So 2 plus 30 is 32. 32 plus 36 is 68. 68 plus 200 is 268 plus these two is 270. So if you approximated, you would have gotten 270 kilojoules, which is really close to the true value of 274.8 kilojoules. So you can tell that this problem is very much involved, but it really helps you learn how to use a heating curve to solve a problem like this. Wonderful. Now, our next objective is going to be on phase diagrams. As we understand how heating curves illustrate the energy changes and temperature behavior during phase transitions, we can further expand our analysis by examining phase diagrams. Phase diagrams provide a comprehensive view of the states of matter and their transitions at various temperatures and pressures. Now, phase changes represent a transition between the different states of matter, solid, liquid, and gas. And we saw this earlier a little bit when we were discussing endothermic and exothermic processes. Now, phase diagrams are charts that show the state of matter under different conditions of temperature and pressure. Now, the x-axis is typically temperature, and the y-axis represents pressure. This diagram is also divided into regions that represent the different states of matter. So here we see our solid phase, and over here we see our liquid phase, and then here we see our gas or vapor phase. In addition, the lines at the boundaries in the diagram, these represent the conditions under which two phases can coexist in equilibrium. So for example, this line right here, this represents the conditions in which the solid and liquid phase can coexist in equilibrium. This line right here represents the conditions in which the solid and gas phase can coexist in equilibrium. And then this line right here represents the conditions in which the liquid and gas phases can coexist in equilibrium. Now, in addition, you see a point right here. This is called the triple point. The triple point is the unique condition of temperature and pressure where all three states of matter can coexist. In addition, there's another red point right here. This is called the critical point, and the critical point represents the highest temperature and pressure at which the substance can exist as a liquid. Now, beyond this point, the distinction between liquid and gas phases disappear, and the substance becomes a supercritical fluid. Now remember that these phase changes are usually reversible. So for example, condensation is the reverse of vaporization, and freezing is the reverse of melting. The exact temperature and pressure at which these changes occur depend on the specific substance you're considering. So that is an important thing to keep in mind. Now with that, we can move into our next objective, which is going to be on Hess's law, but we're going to continue that in the next video. So for now, that's all I have for you. I really hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.